Okay, so in this video, we're going to look at solving circular functions. It's actually the second video of solving circular functions that I've done. Same questions, same examples. It's just that they're two different methods. The first half is the same, the other half is a bit different. So if you want to look at the method on the left-hand side of your screen, that has been done in a previous video, method 1, I've called it. We're going to look at method 2 now. Method 2, I think, is a little bit cleaner. But maybe not as intuitive to start with. It certainly looks a bit nicer, and I think having done this one a bit more now, I prefer this one over the other method, even though the other video I said different. Hopefully this video will be all right. This is the second time I forgot to share my screen last time, and I recorded myself staring at the computer for 20 minutes. So hopefully it's a better video for you guys this time. Regardless of which method you choose, you must be able to do your exact values. So make sure you know your exact value table. However you remember it, doesn't worry me, but you must know these values. If you don't know those values, you don't know anything with circular functions, solving them by hand. Now, whichever method you choose, you get the first 3 steps being the same. The first thing is to isolate your sine, cosine, and tan, get them by themselves. Then find the reference or the base angle, which comes from this first column here. If you're in radians, normally we're in radians. And then we find solutions in our first period. At that point, it diverges. So like I said, other video is these ones over here. We're going to forget this for now. And we're going to do step 4, 5, and 6. So we have to apply transformations to domain. So anything related to the x value, so dilations from the y-axis, horizontal translations, or reflections around the y-axis, we need to apply those to find what we call the working domain. You'll see how that works. Anything to do with the y value, like vertical translations, stretching vertically or flipping down, don't worry about those as we go through. So that's your first step. Then you're going to add and subtract multiples of 2 pi for sine and cosines, or pi for tan. That's to do with their period. The basic period of a sine graph is 2 pi. Basic of a tan is pi, so we add those or subtract those depending on domain to fill out our working domain, and then we solve for x. So let's see how it works. First step, let's get cosine by itself. So you have cosine of 3x will give you 1/2. The base angle here, cosine of what gives you 1/2? Well, that's going to be pi on 3. Hopefully you know those off by heart at some point, but for now you can use the table if you need to. Notice I didn't write x equals, I just wrote BA or base angle equals. I'm intentionally not writing x in there because it's easy to write x and then get yourself messed up. Particularly if theta is written in here, it's easy and tempting to write theta, but I'd write BA or base angle, something else to keep your mind away from the variables. Once you have that, we now need to think in terms of quadrants. Where is cosine positive? Well, cosine is positive in the first and fourth quadrants. And the size of this angle in here is pi on 3. And the size of this angle here is also pi on 3. And now we're at a point that we can find all the solutions in our first period. So 3x will equal, well, if I'm going, I always go from the positive x-axis anti-clockwise. If I'm going around that way, I come across the solution at pi over 3. And then I go all the way around and come across this one. But this one can be described as 2 pi all the way around back that pi over 3, which is given by 2 pi minus pi on 3. And then I simplify that to give you pi over 3, comma, 5 pi on 3. And in the other video, I continued and divided by 3. In this one, I'm not going to. We stopped that. That's our first period. All the solutions in our first period. Now, at this point, I'm going to apply the transformation to my working domain. Remember, this thing here is a dilation of 1/3 from the y-axis and squishes my graph in. But that also means that the domain here has been squished in. So what I want to do is unsquish it. And the way I do that is by multiplying by 3, which, remember, multiplying by 3 is really dividing by 1/3. So I'm actually undoing this dilation of 1/3. Now, if I multiply this by 3, we end up with a domain that looks like 0 to 6 pi. which just tells me I'm going around the circle 3 times. Because remember, our unit circle going around once is 2 pi. So every time I'm going around, it's another 2 pi, another 2 pi. And we do it 3 times to get to 6. So I'm going to start with 3x here equals pi on 3 and 5 pi on 3. That's the first time around the circle. Done. I'm going to go around the circle again. Because if I go around the circle a second time, I'm at 2 pi. I want to go around again to get to 4 pi. So I'm going to go around a second time. But I'm told to travel all the way to 6 pi, so I'm going to go around again. So I've gone around 3 full times, and each time I've picked up this solution in here. Once, and that one there once, every time I've rotated around. So I have to finish off by adding 2 lots of 2 pi. I've gone around twice. So you got plus 4 pi, and I have 5 pi on 3 plus 2 lots of 2 pi there. And then I add all those and simplify all those. 2 pi is the same as 6 pi over 3, so you end up with 7 pi on 3 there. 11 pi on 3 there. 4 pi is the same as 12 pi on 3. So that gives you 13 pi on 3. And that will give you 17 pi on 3 like that. And then at this point, I unsquish that graph. So I'll put the squish back onto it. I get rid of the 3. So we multiplied it out and unsquished it, stretched it out, and now we're squishing it back in by dividing by the 3. So I can have x by itself. So remember, dividing by 3 means you multiply the denominator by 3. If the denominator gets larger, your fraction is going to get smaller, as long as we don't change our numerators. So dividing by 3, and we end up with our 6 solutions there, which we can check to make sure they fit in our domain by looking at our domain up here, our actual domain in terms of ninths. Well, we can't go past 2 pi. That's the same as 18 pi over 9, which is bigger than that, so we're all good. That is how we use the other method. So let's try it with the other 2 examples. First step, sine of 2x by itself. Sine of 2x gives you negative root 3 on 2. And the base angle for root 3 on 2 with sine is pi on 3. This one's a little bit different because I'm dealing with negative values of sine, which is there and there. This one in here is pi on 3. And this one here is pi on 3. Sine is negative in these quadrants. And remember, the way we come up with our solutions, remembering, of course, that 2x must go there exactly as it is. I'm not going to get rid of the 2, you've got to carry it through. Is we start from here and we go around, it's pi plus the pi on 3. And you've got 2 pi minus the pi on 3, which we did before. And that's going to give me 4 pi on 3, 2x equals, and 5 pi on 3. Right, so we found our first period of solutions. Now, let's find the rest of them. But before I can do that, I'm going to have 2x equals 4 pi on 3, 5 pi on 3 there. Before I can go any further, I need to know the working domain. This is my actual domain of my squished graph. I want to unsquish it. This is a dilation factor of 1/2, remember. So I need to multiply this 2 to remove the dilation factor. So we end up with, so times by 2, negative 2 pi, comma, 4 pi. This becomes our working domain. That means I've got to go around the unit circle once, that's 2 pi, again, which is 4 pi, but I can also go backwards from 0, 2 pi. That's what it's asking me to do. So here I am, 4 pi on 3, 5 pi on 3, go around once, I go around 2 pi, that's great, and I've collected these 2 solutions. But I need 4 pi. So I'm going to go around again, and notice I collect those 2 again, but from here, all the way around once is another 2 pi. So I've got 4 pi on 3, plus that, whoops, that's a terrible way of writing 4 pi and 3, plus the 2 pi. And 5 pi and 3 plus another 2 pi. That's as far as I want to go forward because I've gone around twice and I've got to 4 pi. Now I want to go backwards. So if I'm at 0 and I go backwards, like that, I'm going to pick up these solutions. So I've got 4 pi and 3 minus 2 pi. So this one here, I've gone all the way back around to here, and I'm going to end up with 5 pi and 3 minus 2 pi, which I'm going to run out of space to get to as well. And we're going to end up simplifying all these. 2 pi is the same as 6 pi and 3. We had that before. So 4 pi and 3 minus 6 pi and 3 gives you negative 2 pi and 3. I'm just going to reorder them in terms of numerical order. 5 pi and 3 minus 6 pi and 3 gives you negative 1 pi and 3. And now we go left to right. So 4 pi and 3 minus 6 pi and 4 pi and 3 stays as it is. 5 pi and 3 stays as it is. And now I add these ones. So 4 pi and 3 plus 6 pi and 3 gives you 10 pi and 3. And then we have 11 pi and 3. That is our stretched out graph. We want to now squish it up again and apply that dilation of 1/2. So we divide it all by 2. So the 2 cancels, all the even factors will cancel with 2. All the other ones, we're just going to increase the denominator by a factor of 2. So dividing all by 2, and you end up with these 6 solutions. Once again, you always want to check to make sure your solutions are in the domain. Our biggest value is 11 pi over 6. So 2 pi is the same as 12 pi over 6. So that fits, great. Our smallest value over here in terms of pi on 6 would be negative 6 pi over 6. Or you could have negative 3 pi on 3, and that well and truly fits inside, which is good. Our last example. We're going to start, let's say, doing the same thing by getting tan of pi x by itself. So we subtract the 5, divide by the negative 4, and then we find our base angle. And that will give you pi on 4. Cosine is, cosine, I'm doing a tangent. Tangent is positive in this quadrant here and this quadrant here. So pi and 4 there, pi and 4 there. And all solutions in our first rotation. With tan, you don't have to worry about this much because tan is has a period of pi as opposed to 2 pi. So don't forget we used 2 pi for sine and cosine because the basic period for sine and cosine graph is 2 pi without any dilations. Tan graph, it is pi. So I'm just going to find the first solution. I've got pi x down here. I'm going to bring the pi down as well, equals pi and 4. Now what's my working domain? Remember, we're going to multiply it by pi for our working domain, because again, it's a dilation factor of 1 over pi. We're trying to undo that. We multiply it out. It goes from negative 2 pi to pi like this. So I'm going to have pi x equals pi over 4. If I add pi to pi over 4, it's going to be bigger than pi, isn't it? Starting with pi, adding something makes it too big. So I don't want that. I actually need to go backwards. I need to go back this way around our unit circle. So I'm going to have pi over 4. I'm going to go back pi. And then I'm going to have that one and go back another pi. So we go back 2 lots of 1 pi. I've gone back 2 pi, full circle around. I've got this one here and this one again. So I've gone back 2 pi for that, 2 lots of the 1 pi. I'm going to simplify all of that. So pi over 4 stays as it is. Pi and 4 minus pi gives you negative 3 pi and 4, a bit of fraction work with pi's. And this one gives you negative 7 pi over 4. Because remember 2 is the same as 8 over 4. And to complete this question, we're going to divide it by pi. and I'm going to put it in numerical order just to tidy it up a bit. So negative 7 over 4, negative 3 over 4, and positive 1 over 4. We can do a quick check to make sure we haven't fallen outside our domain, have made a simple mistake. Negative 2, our smallest part of the domain, that is the same as negative 8 over 4, which is indeed bigger, which is good. And 1 over 4 is definitely less than 1. We can quickly check to make sure we haven't missed it. Notice the pattern, we've gone up 4 in the numerator, gone up 4 in the numerator, go up 4 again, we'll give you 5 over 4, which is too big, that's bigger than 1. So we've got all of our solutions. And that is how you're going to solve circular functions using a working domain approach as opposed to just adding the actual period of each one. I hope that helps. Let me know in the comments which you prefer.